Okay, Chem 2342, here is Chapter 17, Part 3, Synthesis and Reaction. So the first thing we want to do is we actually want to make some carboxylic acids, which we have done before. We've actually taken alkenes like this and chopped them in half using potassium permanganate to create a carboxylic acid. Note, we get a carboxylic acid from each side of the double bond. So if it's a symmetrical double bond, we'll get a symmetrical acid. If it's unsymmetrical, we'll get two acids there. Another way to do that is to generate it with ozone. Note that this ozone will also create two carboxylic acids if it's an unsymmetrical molecule, but it'll create one if it's a symmetrical molecule. So note the ozone will also break triple bonds to make the carboxylic acid, and if it's a double substituted alkyne, it'll create two different carboxylic acids, and if it's a terminal alkyne, it'll create a carboxylic acid and CO2. Now, this ozone reaction is very important because if we had a benzene ring with an alkyl group and we used ozone as the oxidizer in the system, it's going to oxidize out the benzene ring, leaving the alkane available to us on the main chain. One of the carbons from the benzene winds up in the carboxylic acid here in reaction number 4, and the other carbons of the benzene are actually oxidized away as CO2. However, if we want to oxidize the R group that is next to a benzene ring, it has to be that benzylic position, we can use potassium permanganate and it'll oxidize off any chain. So if you had an ethyl group there, it would still convert it to the benzoic acid. So we've also looked at these in Chapter 12 where we had aldehydes. We could further oxidize them down to carboxylic acids using a silver salt. It's also known as the silver mirror reaction. But we can also do permanganate to oxidize any primary alcohol down to the carboxylic acid. Note the total number of carbons remains the same in both of these reactions. The carbonyl carbon or the carbon next to the oxygen remain on the main chain. Okay? So we can also take either one of those reagents, the aldehyde or the alcohol, and convert it with chromic acid or any one of the Jones reagents to get it down to the carboxylic acid as well. Okay, now here's an interesting reaction number 5 here where we can do a hydrolysis of a cyanohydrin to create a carboxylic acid. Note when we use the hydrogen cyanide in this reaction, it is the nucleophile to create this cyanohydroxy compound by addition, and then by hydrolyzing the nitrile to give us the carboxylic acid, we have gained a single carbon on the chain, but now we have an alpha hydroxy carboxylic acid. So this is a unique structure. Now, when we use nitriles as a nucleophile to displace an alkyl halide, we will be adding a carbon to that chain. So if you're looking for an easy way to add a single carbon to have a product with a carboxylic acid in it, the best way to do that is to use a nitrile here to displace your halide to get your alkyl cyanide compound. Then you can hydrolyze that with water, acid, or base and heat to create the carboxylic acid or the carboxylic acid salt. Again, you're adding a single carbon to this chain, so it's a great synthetic tool to add additional carbons to your carbon backbone. Okay, we can also do that same single carbon addition by using a Grignard reagent and reacting with CO2. CO2 is just 2 carbonyls. It's going to do the exact same thing where the central carbon is partially positive and we'll have the carbanion come in and attack it to add across it, and then after hydrolysis with acid, we will regain that carboxylic acid. Note, you can use any Grignard reagent at all to be able to do this, from primary through tertiary alkanes, allyls, benzyls, or aryls. Anytime you can make a Grignard reaction, you can add this carboxylic acid to it. Another way to do it is you can hydrolyze acid chlorides, anhydrides, esters, amides, and nitriles. All of these can be hydrolyzed under acidic conditions, and the nitriles can also be hydrolyzed under basic conditions. Okay, so what can we use these carboxylic acids for besides just using their acid? Well, the first thing we can do is we can use them as we can deprotonate them to make them into nucleophiles. So most of the carboxylic acids have pKa's of around 5, unless there's some electron withdrawing group nearby. And we can look at these conjugate acids as that once they are deprotonated by the system, that they can be used as that thing. So we're looking at any base that has a conjugate acid that is weaker than that of the carboxylic acid, and we can deprotonate this. This means we can actually deprotonate with very mild bases. For example, bicarbonate, ammonia, carbonate, the sodium methoxide, sodium hydroxide, sodium ethoxide, and sodium hydride. Those can be all used to deprotonate the carboxylic acids found here. Okay. Note, if we do have withdrawing groups, electron withdrawing groups close to the carbonyl, we do have an inductive effect which increases acidity. If we look here on the right side at the bottom, we have acetic acid, which has a pK of around 5. By adding a single electron withdrawing chloride, we've dropped it to near below 3. By adding a second chloride, we've dropped it to below 2. And by adding that third chloride, alpha, to that carbonyl, we've decreased the basicity or increased the acidity of the system. Therefore, we actually have a much stronger acid with this halogenated carboxylic acid compared with the unhalogenated conjugate. Okay, so how are we going to use these things? Well, one thing we can do with these carboxylic acids is to attack them with other nucleophiles. And so what can happen is a couple different things. Once we attack our carboxylic acid or carboxylic acid derivative with a nucleophile, we now have to think about, oh, what is our leaving group? Is Z, the other compound on there, a good leaving group, or is it a bad leaving group? So if we think about that, we can say, well, certain things, like in an aldehyde or a ketone, we would have a hydrogen or a hydronium, a hydride or a carbanion as the leaving group. Now, neither one of those are good leaving groups. So in the case with aldehydes and ketones, we actually undergo that nucleophilic addition, and we do not lose the hydrogen or the R group because they are poor leaving groups. Alternatively, if we have these acyl systems where we have, instead of a hydrogen or a carbon, we have hydroxide, chloride, an alkoxide, or an amine, now we have to compare and contrast what is the better leaving group. Sometimes the nucleophile will displace the hydroxychloride, or that, or the nucleophile itself can be irreversibly removed. Okay, so we need to think about if that our Z group is a good leaving group, it can undergo a substitution reaction, not an addition reaction found with the aldehydes and ketones. Okay, so let's talk about different types of reaction here. And the nucleophilic addition and nucleophilic acyl substitution involve the same first step. The nucleophile attacks the electrophilic carbonyl and to form that tetrahedral intermediate. Now it all comes down to what happens next, okay? Aldehydes and ketones cannot undergo substitution because the hydride or the anion, carbocation anion, are poor leaving groups, and therefore they do not act for substitution, they only act with addition. Now, in contrast, if we have a carboxylic acid, we have OH as a leaving group. If we have an acid halide, we have chlorine as a leaving group. If we have esters, we have alkoxide as its leaving groups. As long as the nucleophile is a better nucleophile than the group that is leaving, you'll end up with substitution of the acyl attachment group with the nucleophile to give us our products. So you have to think about whichever leaving group is better will be the one that's eliminated.